In this video we're going to take a look at some of the challenges from day 4 of the HackTheBox Cyber Santa Capture Flag competition. So each day we've got 5 new challenges being released, one from each category, and I'm doing these videos in order of the number of solves. So normally web has the most solves by this stage, but this time around it's forensics. We've got this challenge called Giveaway, and the description says Santa's SOC team is working overtime during December due to Christmas phishing campaigns. A new team of malicious actors is targeting mainly those affected by the holiday spirit. Could you analyze a document and find the command and control server? So we have a document obviously to download. It is a docm Microsoft Word 2007 Plus. So we could go and open it up and take a look at it. Sometimes if there's macros and stuff, you might need to use Windows or use a sandbox with Windows to try and access some of the, to try and run some of the scripts on it. We can go into macros here, edit macros, go and take a look through. Okay, so here at the auto open, you can see that we have some stuff. We've got some obfuscated code in here, which we could go through and try to deobfuscate. There are some tools that can help us do this. So I actually used OleVBA as a tool here, but there are other tools like ViperMonkey, which sometimes is a bit more successful for me. Let's try and run OleVBA, or you can do OleVBA 3 as well. I'm not really sure, I've not really noticed much of a difference, to be honest. But if we do that with the Christmas giveaway doc, it comes back with some of the macros here, so some of the same code that we were seeing, but it's also given a list of suspicious indicators and some auto exec functions. And we've got some indicators of compromise here, so an IP address and exe name, some suspicious base64 strings, and it's telling us it might download more files from the internet. So you can see here that we've got an option to decode to deobfuscate some of the strings, or we can just go and try to base64 decode them ourselves. Let's try and run it again with decode. We run it again, we actually get some strings this time, so you can see it looks like saying inject. We have hell here. Do we have anything else decoded? There's quite a lot more code up here. You can see that this is selecting characters, some of them by decimal, some of them by their ASCII code. You can see a bit more about what it's doing up here. So there'd be quite a lot to decode manually here. Let's run this again. We also had another option here to deobfuscate. So we can decode, we can also deobfuscate specific strings. Let's try that as well. Missing a space. Try that again, and we can see that we've got some more stuff here this time, and it's concatenating some of these characters, and it's given us these results over on the left. So that looks like we're starting to build up a flag. Let's go and start to put this together. So we have this is, and we have another underscore here, and then once for, and then there was another closing bracket. Now obviously that isn't our flag, it's not a, doesn't make any sense, and it's ending with an underscore. So we need to go and at least decode some of this manually. Let's go up to some of this code up here, and we can see a few keywords here. We can see everybody, present, and Christmas. If we go back to our flag here, this is something once for Christmas. So we're still missing some of this. We've got a present. Okay, so this is a present. Everybody once for Christmas. But that's not our flag. There's also some other stuff happening here. We don't really need to understand all of it, but we can see it's doing some replacements here. So in this case we've got present, it's replacing the e's with 3's. So we'll just go and do that. And then for everybody it's doing the same thing, replacing that with 3's. And the string that it assigns, so it's assigning this string to be equal to everybody with the e's replaced by 3. And then it's taking the same string and doing the same thing again, but with an O and a number O. Number 0. So let's do that as well. So 3, 3, and then 0. and then we're just missing Christmas. So it's going to replace I with a 1 and then A with a 4. And that's our flag. Be interested to hear how other people solve this one. Whether you kind of combined this tool and some manual analysis of this section of code, or did you go through the full macro or run it in some kind of sandbox to try and get the flag. The next challenge is called Elf Directory. It's a web challenge, and the description says, can you infiltrate Elf Directory to get a foothold inside Santa's data warehouse in the North Pole? So we don't have any source codes downloaded for this one. Unlike the previous challenges, we've just got a Docker instance to connect to, so let's go and take a look at it. We're going to have a look. We've got a login form. Because we don't have any source code this time, we'll have a quick look at the page source. Nothing much here really. Maybe we could look at the JavaScript. It just seems to be some kind of form validation on the email. So nothing interesting happening there. Let's try and log in with some default credentials. We could try admin, admin password, etc. We could try and do some SQL injection here. So let me make this visible. So if we do something like, maybe I need to set that to, type. There we go. So yeah, if we do something like this, close off whatever SQL statement's being done to grab the password, and then say, or 1 equals 1. Or you could do something like 1 equals 1, and then make sure you comment out the rest of the statement, however that's done in that language, in whatever language you're looking at. But yeah, this doesn't work for us, we get invalid, but we do have an option to go and create an account. Let's create an account. I always normally try to see if we can add the admin user just to see whether there's already one present with that username or not. And in this case there isn't, so we can try to log in now. So we've got through to this profile page, we've got our username here, admin, we've got some details which we can try to fill in here, but we don't have any option to send off a form. Sometimes that'll just be a case of maybe we need to inspect the element, and maybe it's just disabled or something like that. Maybe there's some script which is disabling it, and maybe we can still use the form without any client-side controls. So maybe the PHP file that allows you to update these or upload images or files or stuff like that is still accessible, and you could go and create a post request in Burp Suite or something just to try and send that off. In this case, what we'll do is hit F12 again. Let's go and have a look at our storage, and we've got a PHP session ID. So we can go and base64 decode this. You can take it to CyberChef or base64decode.com, or you can go to decoder here in Burp Suite, decode as base64, and you can see here we've got this username admin approved. It's actually got some issues here because of the URL encoding. So we can, is there a decode as, okay, that doesn't have a URL safe base64. Let's go to HackTheBox. HackTheBox is doing a URL decode, so you can see here that it's decoded it properly. And now we're going to want to URL encode a new version. So let's see if we can change this approved to true. Okay, we can't update that there. It's very hard to take a copy of that. It would be good if you could just update this and it would automatically update the other side. Maybe you can do that if somebody can let me know. Otherwise I'm just going to double click this or just click that and then paste this in. This is going to give us a URL safe encoded value. We want to update this to true to say we are approved. Replace that, hit enter, and then let's try and refresh the page. Okay, so now we've got the option to upload our profile picture. We can choose a picture here and try to upload it. What I'm going to do is go and grab a web shell. Let me just locate shell.php. I'm going to grab this one, copy it to our local directory. And this is just literally the most basic shell you can get. It's just going to take a command from us and then it's going to call system on that command. So let me try to upload that and see if it allows it. We hit upload, and we get an error. It's hard to actually see here, but we get an error saying invalid image, only PNG images are supported. So I'm going to go over to Burp Suite. I'm going to go to the proxy tab and the post request that we just made. Send that to the repeater, and now we can go and play around with this request. First thing you might want to do is try and change the content type. So it says we're not allowed to upload anything but a PNG image. What if we change this to image/PNG or image/JPEG, whatever it needs to be? But we still get a message saying no, it's invalid. So we could try and change the extension to PNG. Send that off, and we also get a message saying it's invalid. Note that this wouldn't have actually worked for us anyway. If it was just searching for a PNG extension, maybe you could try something like .png.php, but we do need PHP at the end if this is going to be interpreted. So the other thing I was thinking here was the magic bytes. As we did on another challenge, we can look for the magic bytes for PNG, and we could literally go and modify our PHP shell. So if we just open up shell.php, we'd need to add like 8 bytes in here. So 1, 2, 3, 4, 1, 2, 3, 4. I think that was 4, that might have been 9. But anyway, I'm not going to do this because this didn't work for me. I did try to, you can insert some here, then do save, and then hex edit, and then just modify these first 8 bytes with the PNG header. In fact, let's go ahead and do it anyway. We'll try it out. So let's look for PNG. It's this one here. I'm going to take a copy of that, and let's paste this in. Let's replace those first 8 bytes. Let's save it. Yes. Okay, and now if we print this out, we've actually got this PNG header at the beginning. I thought it would have actually said PNG though. Maybe I've done that wrong. 0A, 1A, 0A, is that what we had? 0A, 1A, 0A. That's not what we have. Okay, let's try this. 8, 9, maybe you can't copy and paste like that. 5, 0, 4E, 4, 7, 0D, 0A, 1A. Oops. 1A, 0A. Save that. And that's looking better. Maybe I did this wrong earlier then. Let's try this out and see if it works. I found another way to do it anyway, but let's try it. Upload. Seems to have come back with the same error. Let's go and double check that. It might just still be. Yeah, it's invalid. Alright, well let's send it to the repeater, this one. Do the same sort of stuff here. Let's change this to image/PNG. Nope, invalid. Let's try and add the .png in here. And still invalid. So we need a valid image. And what I did here was open this image up here. We're going to need to know this location anyway, so let's go and open this up. It's in the uploads directory. Alright, we'll save this image. Save it to the same location. And let's go back and upload this. Just make sure it works first of all. It does, it says it's updated, and this is going to be our new profile image then. So let's go back to the repeater, or well, let's go back to our Burp Suite. Let's send that new request to the repeater. And because we've got a valid PNG image here, what I'm going to do is I'm going to rename this to .php because we want to interpret it as a PHP file. But we need some PHP code in there as well, so we're going to grab this shell, and I'm just going to paste this in anywhere. I'm going to hit send. Alright, follow the redirections, all looks good. Let's try and reload the page. Still looks okay. Let's go and open this. And here we go, it's PHP. Well, it has our PHP in it, should I say. So because our PHP shell is looking for a command, it's looking for a get parameter called cmd. Let's do $cmd equals ls. And you can see here then, it's listed out the files in the directory. So now we just need to traverse the directory. I'm just going to maximize this so we can see a little bit better. So this is where our output's going to be. Let's do ls .. and now we can see all of our files in the web directory. Let's do another .. and now we can see this flag something.txt. So we can just take a copy of this and say we want to cat that flag file, and it should have printed our flag. Where's it printed it? Oh, sorry, we need to make sure we still do .. and there we get back our flag. HackTheBox, break, auth, get shells. The next challenge is called upgraded. It's a reversing challenge, and the description says the elves have learned from their mistakes and are now using military grade encryption to protect their secrets, but they've made a critical error. So we download the files. In this case we have output.txt and upgraded. Make sure upgraded is executable, and let's print out the output.txt. We've got some bytes in here. We could go and try and find out how many we've got. I think it was actually 46 or 48 bytes, I think. And if this is encrypted as they mentioned in the description, presumably with this file, because that is what would make the most sense, we know that the first 4 bytes of whatever's been encrypted is likely to be HackTheBox and the curly brace. So that opens up potential for some brute forcing, but we need to go and have a look at the program and try and work out exactly what it's doing. Let's try and run upgraded, enter in secrets, retrieving wishlist, wrapping up gift. Alright, so we enter in some input and it encrypts it. Let me try that again. Let's do HackTheBox. I want to see whether the beginning bytes match up with that output. Doesn't look like it. No, okay. So we could try to run this with ltrace, with GDB or something like that. I prefer to go and take a look at the code in Ghidra first of all. I don't have this imported. Let me skip through the process. It takes a little while. Okay, so with this opened up, we can go and have a look first of all at our functions, see if we've got a main, which we do, and what's going on here. We know that it was taking an input from us, this IO scanf. It's then going to print out a couple of times just to say, just some print statements with some sleeps in between them, so nothing important. The real interesting stuff is going to be down here with our encrypt function. So encrypt is being called, and then we have this cipher, which is being created, a new cipher. It's going to be, it's an AES 256-bit CBC, cipher block chaining mode, and we've got initialization for the encryptor, and we've got an update, and we've got a final X. So if we highlight some of these things here, let's see what it's taken in. You can see that whenever it's initialized, let me take my hand off the mouse, it's very sensitive. Whenever it's initialized, it's going to take in this cipher, it's going to take the type of implementation, it's going to take the key and the IV. So the key and the IV sound particularly interesting, which is in RDX and in RCX. What we might want to do here is set up a breakpoint at this function and see what's actually happening when it's called. So we can just take a copy. Pi is on here, so we're not going to be able to just provide the actual address of this function, but we know what the offset is to that function in the binary. So if we go GDB-PwnDbg, pass in, what's it called, upgraded, have a look at our functions here. We could disassemble here if we need to find offsets and things like that. So these addresses are just offsets to the different functions, but as soon as we run the program, and then let me just do info functions again, it's going to show a lot of functions, but essentially it will now have resolved these addresses. Let's do disassemble main. So you can see it now has the actual addresses, but the offsets are still the same each time. Anyway, we wanted to do that break RVA, which if you just, oh, I didn't mean to do that. Let me delete breakpoints. I meant to bring up the help. So if you do break RVA help, this is just gonna set a breakpoint at a offset from the Pi base, and we just provide the offset here. So we say break RVA 0x, and then that address that we copied, that's where the encrypt is gonna initialize. We'll hit run. Just type something in here, test, and it's going to run through, and whenever it gets to that address, we're going to hit this breakpoint, and we can see we've got test here, we've got some values which look to be of interest, but let's go and see here the actual parameters. So we can actually see here the values that we had in Ghidra. Let me maximize that so we can see that in the background. So what was being passed in here, the in RDX and the in RCX was our key and our IV, and we have the key and the IV right here. We've got the implementation, the cipher, and all that sort of stuff. So we could grab this here, but that's not going to be the full length of the key. So let me try and do, let's print this out here. Let's try and do x over gx. We'll print a bit bigger. Let's do x over 4gx, and that'll print out some more information here. And we can basically hopefully go and just plug these values into CyberChef and get it to decrypt. We could also go and set up some breakpoints and see what's happening in these other stages as well, which I did actually do whenever I was doing this, because I did run into some problems using the values that we have in GDB. But we can also identify this manually as well. Let's go back to the main function. We know this has taken the in RDX and the in RCX, so let's go and see what's in the RDX and the RCX before the crypt function is called. So we have encrypt right here, and just before encrypt, you can see our code, our assembly code over here. So just before encrypt is called, we have this value which is being placed into the RDX, value to the offset of 40. That's being placed in the RDX, and then the RDX is being moved into the RCX, and then the RDX is being loaded with this value 1 at the offset of 20. So our RCX, it looks like, is the, our RCX was the key, right? So our key is beginning at the offset of 40 here. You can see all these hex bytes, 6B, D5, 5277. Let's go back here to GDB. 6B, D5, 52. So this is why this wasn't working for me. It's the order of this needs to be reversed. 6B, D5, 52 is the endianness, which I did actually try to do in CyberChef, but I had some problems doing it. So I'll show how I grabbed these addresses in a second. But essentially we know this is the offset here that we're going to be interested in. And then for the other one we can go and have a look at value 1, the offset of 20, and that's going to be our, was that our key? That's going to be our key, yeah. And then this one's going to be our IV. So let's go and see how we could do this in another tool. Go and open up Radare and do R2 upgraded AA AFL to list the functions. We don't really need to list the functions, it's the sections we're going to be interested in here. So I, then capital S for the sections. Let's go back here. This is probably in the data section. Okay, I'm just going to take the address. Let's go and get the address for the first one was value 240. It's this one right here, so we can actually just grab this offset again and say that we want to access this offset. We can do px 0x, paste that in. Do I want to print all the lines? No. Okay, well, yes I do, but we're going to have to scroll up here a bit. Alright. I'm not very good with Radare. There'll be a way to just print what you need to there. But what was the offset that we just wanted to look for? 4148. So just have a look up here. 4140. So it's going to be here, isn't it? 587, etc. And we're going to go stop plugging this stuff into CyberChef. So I'm going to open CyberChef. Let's do AES decrypt. We know it's CBC mode. We'll go and get our output.txt, which is our ciphertext. Paste this in here, and then our key is going to be, I think this is our key that we're doing first. Let me just go back there to, let's start with our key. So encrypt, we've got our RDX is going to be this value 1, 20, so 40B4, 40B0. So 40B4 is this 9982 onwards. So let's grab this, paste that in there. Hopefully it's not going to mind the spaces. Grab this as well. .44. Okay, that's too many. Let's go back till we've got 32. Alright, looking good. Let's get the IV as well. The IV then is, go back to our encryptor. This is value 240. So it's 4148. It's beginning with 6B. 4148 beginning with 6B. So right here. Take a copy of that. Paste that in there. Do the same again. Oh, there we go. Alright, so we got back our flag. It was HackTheBox hard coding keys rookie mistake. The next challenge is called Meet Me Halfway. It's a crypto challenge, and the description says, evil elves have deployed their own cryptographic service. The keys are unknown to everyone but them. Fortunately, their encryption algorithm is vulnerable. Can you help Santa break the encryption and read their secret message? So we've got a service connect to this time. We've also got a downloadable script. I've just modified the script slightly just to include some comments, but I haven't changed anything else in it. So let's trace this from the beginning, where the challenge is called here. It's going to generate two keys, key 1, key 2, and if we have a look at the generate key function, it's using an alphabet of 16 bytes, so hex value is a hex range here, but these are the bytes that it's using the characters. It's got a const variable here, which is set up a 12-byte password, and then it's basically going to loop through here, so it's saying for I in range of 16 minus the length of const, which is 12, so it's looping through 4 times, and each time it's selecting a random character out of these 16 possible characters. It's then going to return the key plus the const, or the const plus the key, depending which key it is. As we can see here, it passes a 1 the second time, but it doesn't pass any parameters the first time, so it's just going to use 0 as the option. So essentially we've got two keys. One is going to be this const followed by 4 characters selected from here, and the other is going to be 4 characters selected from here and the const, which means we've only got a range of 32 bits, which are actually random for each of the 2 keys. It's then going to perform an encryption. It's actually encrypting the flag. You can see we've got a dummy flag here, so it's encrypting that. It's going to print that out to us so we know what the encrypted flag is, and then it's going to take some input from us. It takes it in JSON format, and the dictionary key is PT for plain text, and then we paste in the value, which is in hex as well. From hex it's being converted from, so we supply that. It's going to encrypt our plain text with those same 2 keys that it's encrypted the flag with, and then it's going to print the result back to us. In terms of the actual encryption here, if you have a look at the function, it's simply doing 2 rounds of AES. So it's going to create this AES cipher with key 1, and then it's going to encrypt our data, making sure it's padded to 16 bytes. It's then going to create this cipher with key 2, and then it's going to encrypt our data again, the one that's already been encrypted with key 1, it's going to encrypt it with key 2. You can see I put a comment here with the address of a meet in the middle attack, so that's the vulnerability we're going to be looking at here. But if you weren't too sure what to look for, let's go and just search for 2-round AES vuln. We'll see very quickly there's a link here where somebody asks, is there any issues doing 2 rounds of AES 128? And somebody has responded here saying double encryption with AES 128-bit with 2 different keys does not give 256-bit security. In particular, classic meet in the middle attack applies with the expected 2 to the power of 128 encryptions and 2 to the power of 127 decryptions. As is, the attack requires ridiculously large amounts of memory, but improvements using blah 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 can improve the speed basically. So we can go and have a look at this in Wikipedia. If you're interested in all this maths and stuff, you can go and have a look through some examples. There's some good videos and stuff out there as well. But what I did here, I found once you know what the attack type is, we can go and search something like meet in the middle, CTF write up, and find some similar challenges. So I went and had a look through a couple of similar ones. In fact, this Byte Bandits one is the one that helped me the most. But what I'm going to do is open up the write-up that I went to because it had quite a lot of good background on this. So if we just scroll down a little bit, similar sort of code. It's got 2 rounds of AES, and their key generation is kind of similar as well. It's basically using a small range of random bytes. We're not going to be able to use the exact same script, but we will be able to go and modify this a little bit. We have a little bit of an explanation here just explaining what we just read, that using 2 rounds of encryption doesn't double the security. And then in terms of the attack that we're going to be using, this meet in the middle attack attempts to find keys by using both the range of the ciphertext and the domain of the plaintext of the composition of several functions or block ciphers, such that forward mapping through the first function is the same as backward mapping, inverse image, through the last functions, quite literally meeting in the middle of the composed function. So in simple terms, we need to encrypt the plaintext with all possible keys, obtaining a set of ciphertext. Let's call that CS. We now start from the ciphertext and try to decrypt it by brute forcing all possible keys until we find the decrypted ciphertext that is in the CS set. Once we found a match, we can stop brute forcing since we've already got our 2 keys. And it's just saying here, did you say brute forcing? It takes time. No, remember the poor choice of keys. So in terms of the range of characters that we have available here, so essentially we can go and brute force through this character range of, we've got 4 possible bytes for key 1 and then 4 possible bytes for key 2. And they put together a script to do this. I basically took this script and went and adapted it a little bit. So let's go and take a look at the script that I put together. So we've defined some of the same values here. We've got our alphabet, we've got our const. I've put in some plain text which we're going to encrypt, and this is the encrypted version. This is going to be different each time, so we need to go and run the program again to get this output, and then this is the output of the encrypted flag as well. So we're basically going to use this plain text. We know the plain text because we're encrypting it, and we know the ciphertext because the program's returning it. We're going to use that to kind of brute force our way through those 4 possible bytes and identify what the key is. And once we've recovered the key, all we need to do is just decrypt the flag, which we know is encrypted with the same key that we encrypt our plain text with. So we've got 2 loops here. We've created a ciphertext dictionary. We're going to loop through this. This product is basically just saying, for the alphabet we have here, create all possible permutations of 4 bytes of these. So that's just a quick way of doing that. I had some problems with this because I was actually using the permutations before that, and permutations will only use one of each character. So for example, a key like F, F, E, E wouldn't be possible. It would only use like C, D, E, F, and etc. It'll only use each character once, which our program isn't doing. So that took me a little while to get that fixed. But essentially then, this is for our key 1, which is the const plus the 4 random characters. It's going to go through each possible 4 characters. It's going to append that to the const. It's going to create a key, and then it's going to encrypt our plain text, and it's going to add the result to this ciphertext dictionary. So by the time this is finished, it's going to have looped through our plain text here. It's going to have encrypted this with every possible variation of 4 of these alphabet characters, and it's going to put each of the keys in a It's going to put each of the ciphertext into this dictionary as a key, with the value being the suffix, i.e. the 4 random bytes that it was encrypted with. And then we're going to do the same thing for the second key. Obviously we do it the other way around, so we're using a prefix, then const rather than const and suffix. We'll do the decryption, in this case, of our ciphertext, because we know we've got our ciphertext here as well. And we'll keep going through and see whether the decrypted ciphertext is in any of the ciphertext we generated using those keys, which it will be because we're covering all possible keys. And once we found that, that means we found both our key 1 and key 2. So we just say this is our winning suffix, this is the 4 bytes which were used to encrypt using key 1, and these were the 4 bytes used to encrypt using key 2. And then we can just go ahead and do the decryption on the flag using those keys. So let's test this out locally first. I'm going to run Python challenge, and it gives us our encrypted fake flag. It asks us to encrypt some text. We need to enter this in as the JSON format with the plain text like this as our key, and then our ciphertext, our plain text as the value. So I'm going to go here and say hex cryptocat, get the hex values here, and we'll submit that as the plain text. We send that off and we get back our ciphertext. So in our script, we just update this and say that the ciphertext for cryptocat this time around was this value here. and the flag which it gave us, oh no, sorry, the flag's up here. The flag was this one, so we paste that in as well. And now if we run our solve scripts, it's going to loop through. You can see that it's found the suffix and the prefix, the correct ones, and it's got back our dummy flag. That's it. We just need to do the same thing against the remote server. Let's take a copy of the server and a port number. Let's connect to it with Netcat. And we need to, here's our flag anyway, so let's grab a copy of that first of all. That's our encrypted flag, and then we need to provide that hex value as well, so it is PT, paste that in. And there we go, so there's our encrypted CryptoCat. We'll put that in as well. And let's try to run the solve script. And the script returned there, we got back a YouTube link, which I didn't bother clicking, it's probably another Rickroll. And we got back our flag. The next challenge is called Minimelfistic. It's a Pwn challenge, and the description says, the elves finally understood what went wrong with their plans. They were too fancy and obvious, but this one is different. It's a security system, but the alarm rings whenever Santa's house is vulnerable to an attack. Will you manage to deactivate it? PS, sound on. So I've already got the file downloaded, and we've got the server up and running, so that once we've got things working locally, we'll go and test it remotely. We've got a lib-c library again, like we did with yesterday's challenge, which is a bit of a hint that we're gonna need lib-c. And we've also got the Minimelfistic. So let's have a look at the binary protections and see what we've got this time. So notable things here, we've got full railrow, so we're not going to be able to overwrite entries in the global offset table. We've got no stack canaries, so we don't need to worry about tripping those off if we're doing a buffer overflow. If we are doing a buffer overflow, we're not going to be able to inject shellcode onto the stack and expect it to be executed. And we've got no pi, so the program addresses are going to be the same every time it loads. So with that out of the way, let's make it executable and let's try and run it just to get an idea what the program does. You can see it's repeating this message, Santa is not home. It asks us, do you want to turn off the something or other? Let's say yes. For your safety, will not be deactivated. And then it goes back to the Santa is not home. It says Santa returned this time. Oh, it said that last time as well. So you had 4 times there Santa is not home, and this time we've got it 3 times. So let's say no this time. And pretty similar, but it just came back with Santa is not home. We could try to see if we can do a buffer overflow here. Can we enter in some really long input? And actually it didn't seem to do anything. Let's try with a longer input again. And nothing. So it doesn't seem to be a buffer overflow at this stage. We're going to need to go and have a look at the code and work out where the vulnerability is. So let's close this down and let's go and take a look at this in Ghidra. We'll go straight over to our main function here and see what's going on. We've got some variables declared here, plenty of variables on the stack. We've got our setup, which we don't need to worry about, just setting up an alarm and stuff like that, which you can patch out very easily. In fact, I don't think I've done that yet in this HackTheBox Santa series. So let me just show very quickly. If we take a copy of this template I have for patching binaries, I'm just going to copy that here, I'm going to open it up, and you can use this to very easily patch out alarms, or in this case I think I have this set up to patch out ptrace, so ptrace can stop you from using debuggers sometimes, and you can basically just replace any calls to ptrace with a return instruction so that it's never called. And in this case we could basically go and say what's the binary name, so we can just grab the binary name, enter it in here, say we want to get rid of the alarm, which will basically set the program to exit like every 2 minutes or something like that. And if we do Python patch binary, it produces this patched binary which will not have that alarm in it. It's not really important for us here, but I just thought I'd show that very quickly. If you ever come across that where the alarm's annoying you, or you need to patch something out to enable debugging or something like that, it's very easy to do with PwnTools. You can do that with Ghidra and even hex editor and stuff as well. But okay, that out of the way, let's get back to the code. So we'll go back to our main function here with the interesting stuff. And we've got this local variable set to 1 at the beginning, and it's saying while it doesn't equal 0, keep going through this code. And the code we've got here, local 18 is being set to this .data section variable. This is just going to print out then the hello, do you want to turn off the alarm? And it's this sec alarm function, which is basically, this looks a bit complicated, it's really not. It's just setting up a random variable based on the time, and it's going to loop through based on these random variables and print Santa is not home until Santa returns, and then it's just going to write that back out. So not really too much of interest to us there. There was no input or anything for us to overflow the buffer, so let's keep going through. We've got this right, I think this was again, okay, yeah, so that's just writing out the message to us. And then we have these variables set up, all set to 0, and then it's going to read in some data from us. So here's a chance for us to actually overflow the buffer, and you can see here 7F0, that's reading in 2032 bytes. And you can see here it's reading it into local 48. Local 48, well, we can see here on the stack, we don't have too much here that we would need to overwrite before we would make it down to the return address. So we can overwrite the instruction pointer. So we should be able to overflow the buffer here, and note that it says here if char local 48 equals 9, it's going to say goodbye Santa, it's going to write that to the screen, and then it's going to set local C to 0. I quite often like to go and rename some of these variables so that you know exactly what's happening. So you could even rename some of these .data sections and say that that is, you know, the prompt or something like that. We could rename variables like this, maybe set the loop counter to be I, if that's what you're used to seeing in your code. And you can keep working your way through and doing that. I'll not do that here, but if you're dealing with particularly complex code, sometimes that can help. So the issue is here, alright, we know there's a buffer overflow because there's not enough space on the stack for this 2032 bytes that it's reading in from us. But the problem is, even if we overflow the buffer, if we never make it down to the return, it's not actually going to overwrite the RIP. So we need to make sure we exit this infinite loop. And to exit that, we need to supply a 9 as the local 48 variable. Then it's going to go through here, it's going to set this to 0 so that the while loop ends, and that way we'll get down to this return address. Why don't we go and just test it out in GDB, and we can try and enter a cyclic pattern and just go and verify things that way. 2032 bytes, so I'm going to do 3000, although there's only like a few items on the stack anyway. Let's try and run it. Oh, we need to select it. And then now we can run it. We need to wait for it to ask us for an input. We'll say 9, and then we want to put in our cyclic pattern. So the first character is going to be a 9, which is going to make sure that we are going to exit the loop, but then we also want to overflow the buffer as well. We enter that in, it said it's exited, gone back to the return address, which is good because it means it's overflowed the buffer. And this time we have SAAA here. Notice that there's an A at the beginning. That's just because we had a 9 at the beginning of our cyclic pattern. So we actually want to say, let's do cyclic-L, look that up, and it's actually 72 bytes. So we want to write a 9 and then 71 bytes, and then the address in the program that we want to return to. So before we go and explore how we're going to put this payload together, and we want to do something similar to the last challenge, right? The last challenge we looked at, we were given a lib-c library, we wanted to leak one of those addresses, and then we want to find a way back to the start of lib-c so that we can then call system with the bin.sh string in it. So last time we did that, we went and grabbed a script from my GitHub which was called Ropstar. I'm going to go get that again, the same one, just to show that we can always kind of use these templates, or quite often use these templates and change relatively little. So let's go here, pwn library Ropstar, and I'm going to open this up in Codium. Let me just grab the file name because I forget how to spell it. I'm going to update this. Let's try and run through this quite quickly. I'm going to get rid of this find instruction pointer offset. This time I'm just going to type in 72 because we know it's 72. We just found it in GDB. And in fact, we don't really need to look in GDB. If we go over to our stack here and have a look here. So we've got all our items on the stack. You can actually see the size of each item and then where it is on the stack. So this is in hex, but you see here minus 48, which is 72 in hex. So 16 times 4 plus 8 is 72, and we can basically work out what we need to overwrite and our offsets and stuff just by looking at this. But yeah, we've got that 72. We haven't updated our binary name. Let's do that now. And let's go and see what else we might want to change. Let's get that return address instruction. I'm going to do wropper again just to look up the gadgets. Get the offset this time. It's 400616. You can also, because we're using ROP objects in here, you can actually use this and say ROP.gadgets and print them all out, or you can use the find gadget search to actually search for gadgets, which is fine. It basically just uses the same functionality the ROPper uses though. And this time I'm going to build up the payload manually instead of just sending it here, because we need to think a bit more about how we do our offsets here and what we send. Rather than just sending a cyclic pattern, we need to send the 9 to begin with. So we can do this flat here again, and instead of using a dictionary, I'm going to use a list instead. And instead of saying the offset was here, we'll say, we're going to do a ROP chain still, but we're going to say send 9 plus offset, plus we'll do no operation instruction, nop times, and then we want to do length of offset minus 1, because I think the offset a decimal? Let's see. Alright, minus 1, and then the next element in our list is going to be the ROP chain. So yeah, this is just another way to put these together. Let's see if that format's alright. It does, looks good. We could also just say 71 here, but yeah, this is fine. Hopefully this will work for us. It's going to do a 9, it's going to do 71, no operation instructions, and then it's going to call ROP chain on whatever we supply here. And again, we're looking to do the same thing. We're looking to leak an item from the global offset table, and then we're going to find our way back to the lib-c base address, and then from there we're going to do another payload where we want to call system. But let's go and have a look at some potential issues here, because you can see we're calling rop.puts here, but if we go back to our code, you'll notice that it's been using writes and reads throughout this rather than puts. So we can go and have a look at our global offset table, and we'll find that actually there is no puts here. There's no puts and there's no printf, which are our two pretty common functions that we would use to print out one of these addresses. So we would be looking to use then write instead. You can see whenever we're writing stuff to the terminal here, what it does is it loads the item it wants to write from the .data section into local 18. In fact, let me just update this. Let's say data, and then this is the data length. And so what it's doing here, it's calling write, and you can see the file descriptor is first, which is going to specify, one is going to specify that it's going to output to us in the terminal, and then the data is second, and then which is the buff, and then n is the length of the data. So we can do something like this to leak out our global offset table address, but we need to specify these three parameters. The way that I did this was to simply try to update our ROP object and say, instead of ROP.puts, do ROP.write, and we want to write out the write address. And let's try and say the same thing. So 1 is the file descriptor, and the length is going to be 8 bytes. So we want to get the first 8 bytes. And then, as usual, we'll go back to the main function so that we can go and do this again and actually do our second payload. We need to make sure we send this off as well. Let's just put in here payload. And let's test this out. I always like to comment out as much as possible so that we can just focus on whatever's at hand and not see a flood of errors and stuff like that. So we'll send that out. We'll go into IO Interactive and see what's happening. Let's try and run Python ropstar. We run through that and we've got an error. Okay, int has no, okay, yes, so just some minor syntax error there. Let's go and do Oh, okay. So offset is already an int, so I'm just going to do times offset -1. We run through that again, and we can't concatenate bytes and strings, okay. So let me just change this to a byte. We run that again, and we've got another error, but this is a different one. So this is saying could not satisfy set registers RDI1, RSI, this is the global offset table address for the write, and RDX8. And the problem is this RDX8, we could go and have a look with Ropper, and you can do Ropper -- file, we can search for, we can search for pop, or we can search for move, we can do different things like that. But basically there's no way, if there was a way for it to satisfy this condition, it would have found it, and there isn't. So we could go and we could try to remove that and run it again, just without the size. And that works. It was able to, oh. Payload is not defined. Okay. So this should work, but it's not going to leak us the address. And the reason for that is essentially that we've not provided a length. So we're saying we want you to write 0 bytes of the global offset table write address to this file descriptor 1. Now admittedly this took me quite a while to work out how to solve this, but if we go back to our code, we have this banner function which we're used to seeing in all these challenges, and I normally ignore it because it's normally just printing out the banner and doing nothing else. But in this case, if we right click it and go to show references to, we'll find that it's never actually called, so it never actually prints the banner. So if we have a look at the banner here, we'll see all it's doing is it gets the string length of this variable here in the data section, it sets that to n, and then it's going to call write with the file descriptor 1, so it's right into the terminal, the banner, but it's never actually called. So let's go and try it out. Instead of doing rop.main, let's do rop.banner. We'll run it again. And this time it printed the banner. Okay, with debug mode on it looks a bit hard to read, but you can see this banner here, it's basically a lock inside like a heart or a balloon or something. And this is something that we can use, so we're not able to set the RAX to the length that we want so that we can call the write operation. But if we can call this banner function, let's have a look here, this is gonna set the RAX to the length of this .data section. It's then going to call write and then return. So if we were to call our write immediately after that, the RAX will still have this length parameter in it. So the only things we'll need to fill will be the 1 and then the address of the global offset table function, which we're able to do in our script, as you can see. Okay, so just to reiterate that, we're going to call the banner first, and then we're going to call rop.write. So once it's finished running the banner, it's still going to have the length in this parameter here. It's still going to have the RAX populated with the length of the banner, so we don't need to worry about not being able to fulfill that condition. So it'll just call write immediately after with our parameter, and it'll try to, obviously, ideally we'd only want to do 0x8, 8 bytes. In this case, it's going to print out the full length of the banner, whatever that is, you know, something like that probably, 256. So we're going to need to receive a lot of these lines before it actually receives our payload here. Let's just demonstrate that as well. We also need to go back to main, because if we don't, it's just going to close the program. So let's try that out. Runs through, and there we go. So it's printed out the banner first of all, and then right after it's printed out the global offset table address for write, and then it's printed out all this other stuff that we don't need because we asked it to print out that much data. So a couple of things to mention. We are going to need to update the rest of this section here. So this section here was currently subtracting the puts address from the got puts, so we just need to update this and say actually the address we're leaking this time is write, but it could be very easily read or something else. As long as you updated the offsets here, that should be fine. And we need to receive all these lines. We'd also want to remove that debug situation there so that we can just see a bit clearer what's going on. I already went through and did this. I'm just going to copy over my script rather than typing it all out on screen. And let me just go through what I've changed here then, which really isn't too much. We've got we call banner, we're going to call write, we're going to call main, it's going to overflow the buffer and call these three in order, and then we're going to receive 41 lines, which is how many lines that banner is. And then the next thing we're going to receive is going to be the global offset table address for the write function. We're going to use that to find our way back to the base of the lib-c binary, and we're updating our lib-c library here so that it knows how to find its way to other functions automatically. And that means we can just use this ROP object again on the lib-c library. So I've changed very, very little from the last challenge that we did. Realistically, you're talking about maybe 6-7 lines that we needed to change this. We've changed the payload format slightly, but really haven't changed too much there. And then down here, we're just duplicating exactly what we did up here, but we're leaving all of this sort of stuff the same. If we run this, just testing it locally first of all with our local lib-c library. I've got this set to info, which is why you're seeing very little output. You can see it's leaked the global offset table write address, it's found its way back to the base address, and then it calls system. We're now logged in with a shell. This is just on the local system, so if we want to test this out remotely, we can go and grab this server address and port number, and we can simply add remote, paste that in afterwards, and the only thing we need to change in the code is to set it to use the lib-c library we downloaded, because that's the same one the server's running. You could actually update the start function here just to easily swap between the lib-c libraries as well, but I'm not going to bother with that. Let's try and run it. We run through that. We've got no end of file, so that's a good sign. We can try and run who am I. We'll see that with CTF we can try to cat flag.txt, and we've got back our flag. So yeah, this challenge a bit of a step up. It did take me a while to solve, because you kind of maybe there was multiple ways to solve this, or maybe that was the intended solution. We'll see. One other thing that I forgot to mention there, I did mention in a previous video, but with these ROP chains, if you're using the ROP objects, you can just go and print out. We can do prettyprint ROP.dump, and I think we did that with the previous example, but let's just actually have a look at this payload because this one's slightly more complex. Let's try and run that. This is just on a local server, so you can see that whenever we dump that out, it's actually dumped out the full chain. And just to talk through that a little bit then, you can put this together very easily manually. So we're calling banner, and then we're going to call pop RDI, so the next value is going to be popped into the RDI. The value is 1, which is the file descriptor that we want to write out to, that's right here. And then the next thing is the global offset table write address, but essentially it couldn't find a pop RSI gadget to just pop this into the RSI. The only gadget available was pop RSI pop R15. So it's selected that one, and then it's just put in the global offset table write address into the RSI, and then padded out the R15 with garbage basically. It's then going to call write, which is first going to look into the RDI and see what's the file descriptor, i.e. where do we want to write it out to, and then it's going to look in the RSI and see what do we want to write out, and then it's going to look into the RDX and see how much do we want to write. And that was the reason we had to go through that banner to make sure that the RDX was populated with the string length of this .data section where the banner is, in order to actually make sure it's printed to screen. Otherwise it would just try to read 0 bytes, or should I say write 0 bytes out. So yeah, you could put this together manually, and you could, if you go through ROPR and do I would really recommend, if you want to learn more about doing these ROP chains, if you go back through the ROP Emporium series that I did, well, try to go through it yourself and then check out the videos afterwards if you get stuck or if you want to see how I solved them. But they really kind of show you the approach of looking for ROP gadgets and what order to kind of trace them from, how you want to build them up. In this case, if we said we know we want to find pop RDI because we want to --search. We know we want to find a pop RDI because we need to make sure the file descriptor is in the RDI register. We also know we want to find an RSI because we want to make sure the data is in the RSI. And we would find that there's only one gadget available, which is this pop RSI pop R15. And that's why it's padded out the R15 with these values. So we could have very easily built this up manually. The main reason I didn't really was just to save time and to show that you can, if you have a script put together for solving these challenges, you can go through and change relatively little and still accomplish the same goals. But yeah, if you want to see how to do things manually, and I recommend that's a great way to learn, definitely go and check out the ROP Emporium series that I put together. Okay, so that's going to wrap it up for day 4 of these challenges. You can see that day 5 has actually started now, but day 5 only has 6 hours instead of 24 hours to do the challenges, and the difficulty is stepped up quite a bit. Let's see what the solve's looking like at the moment. We've got 2 on forensics, we've got 14 on reversing, 21 on crypto, 13 on music notes, and 54 on naughty or nice. Alright, well I'm going to have a look through these anyway. There's a couple of hours left. I'm not sure if I'll get a video done for day 5. Maybe let's see how many challenges I get done and how much time I have during the week. But if not, remember that there will be a live stream on December the 14th with some different content creators going through some of these challenges, so hopefully they'll go through some of the harder challenges from day 5 if I don't get a video done for them. But yeah, I hope you've enjoyed the video. Any questions or comments, leave them down below. Thanks.